Next up, we can have heterocycles. And so these have a non-carbon atom in the ring. And so oftentimes this means that we're going to have some lone pairs in here as well. And so the trick is, will this lone pair donate into this pi system or not? It will donate if it forms an aromatic compound. If it doesn't form an aromatic compound, it won't donate, right? So let's take a look at an example. And we actually covered this much earlier in the semester as well. So this might be a flash from the past, right? So we have this compound right here. This is pyridine. And so we have these 6 pi electrons. And then we have this lone pair on here as well. And so there's different ways you can think about this problem, right? If it tries to donate in that lone pair, it'll be anti-aromatic, and so it doesn't want to do that. And so you can tell that these lone pairs are not in the aromatic system. And in addition, earlier we learned that this is sp2 orbital, so it's not in the ring anyways. But if you just count the electrons that are in the ring, right, that's 6 pi electrons. And so this compound is aromatic. If you take a look at a different compound, this will be pyrrole. Right? This has this lone pair as well. And so if we think about here, we've got 2, we've got 4. We want 2 more, and so we can indeed toss these 2 electrons in here, right? So these 2 will be in the ring. And again, they're in p orbitals, because we can undergo these resonance structures. So think back to earlier in the year, or try to make an aromatic compound, right? So again, here we have 6 pi electrons. We're aromatic. Let's see how this aromatic system and whether it donates this lone pair or does not donate this lone pair affects the chemical reactivity of these compounds. And so let's take a look at pyridine first. And we use pyridine a little bit. It's often used as a base, right? As a base. And so if it's a base, that means it's going to pick up an H+, and it's going to do that with the lone pair of these nitrogens, right? So these nitrogens are going to come in and pick up an H+ to form a protonated version of our pyridine. And so you can take a look in the left or the right system. We still only have 6 pi electrons, and so we're still aromatic. So even though it's behaved as a base, it hasn't disturbed this aromatic system. If we then take a look at pyrrole and try to get it to act as a base, we now ruin our aromatic system, right? We're no longer fully conjugated, and so this is non-aromatic once it gets deep, once it protonates itself. And so because you ruined this aromaticity, this pyrrole doesn't want to pick up this H+. And so this compound on the right is not basic, right? While pyridine is basic. So even though overall they look relatively similar, they're actually almost completely different due to their aromatic properties. You can think of other compounds as well. So for example, we have this cyclopentadiene with one of these oxygens substituted in. And if we think about our system here, we've got 2, here we've got 4. And so we want 2 more electrons to resonate in here, so that way we can make an aromatic system. And so what that means is that the other lone pair is not within our system, and it's not in a p orbital. And overall, this compound is aromatic. So you can think about it as forming aromatic systems, or you think back earlier in the year and think about the hybridization of these compounds, right? If they can resonate, chances are they will, unless you make an anti-aromatic compound. If it forces you to make an anti-aromatic compound, it's not going to resonate within the ring.